The possibility does not prove that life came from elsewhere, but it does suggest that planetary environments may be less isolated than once believed. Across astronomical timescales, worlds may share more than gravity. They may share chemistry, water, and the building blocks of life itself. The chemistry of life in motion, if life can endure extreme environments, and if planetary systems exchange material through impacts and meteorites, then a deeper pattern begins to emerge. The solar system may not function as a set of isolated worlds, but rather as a loosely connected chemical network in which water, minerals, and organic compounds move between planetary bodies over immense spans of time. One of the most striking discoveries supporting this idea comes from the study of meteorites themselves. Many meteorites that reach Earth contain complex organic molecules, including amino acids and other carbon-based compounds associated with biological chemistry. The Murchison meteorite, which fell in Australia in 1969, remains one of the most famous examples. Analysis of this meteorite revealed dozens of amino acids, many of which are rarely found in terrestrial biology. These compounds are not themselves living organisms. However, they represent the building blocks from which biological systems can emerge. Their presence within meteorites suggests that complex organic chemistry can form in space and survive the journey to planetary surfaces. Additional evidence has emerged from comet studies. Observations of comets have revealed the presence of water, organic molecules, and complex carbon compounds within their icy structures. When comets approach the sun and warm, they release these materials into space, forming the distinctive glowing tails visible from Earth. Space missions examining comet composition have confirmed that these bodies contain both water and a range of organic molecules that may have played a role in early planetary chemistry. Together, these discoveries suggest that the raw ingredients of life may be widespread throughout the solar system. Rather than forming exclusively on Earth, the chemical precursors of biology may have been present throughout the protoplanetary disk from which the planets formed. During the early history of the solar system, collisions between asteroids, comets, and young planets were far more frequent than they are today. These impacts would have transported large quantities of water, minerals, and organic chemistry between worlds. Some researchers now believe that a portion of Earth's water may have been delivered through impacts by water-rich asteroids originating from the outer solar system. If that interpretation is correct, then the oceans covering Earth's surface may represent the cumulative result of billions of years of material exchange across the solar system. The implications extend beyond water alone. Organic chemistry arriving from meteorites or cometary impacts may also have contributed to the complex chemical environment in which life eventually emerged on Earth. In this view, Earth's biosphere did not arise in complete isolation. Instead, it developed within a planetary system already rich in organic chemistry shaped by collisions and exchanges between celestial bodies. Over time, the oceans became the central stage upon which this chemistry evolved. Within the deep sea, mineral-rich environments and hydrothermal systems provided stable conditions in which complex reactions could occur. These environments may have helped transform simple organic molecules into increasingly sophisticated chemical networks. Some origin-of-life researchers have suggested that hydrothermal vent systems provide one of the most plausible environments for the emergence of early metabolism. The combination of heat, mineral surfaces, and strong chemical gradients creates natural conditions capable of driving complex reactions. Whether life began in such environments remains an open question. What is clear, however, is that the ingredients necessary for biological chemistry, water, carbon compounds, and reactive energy sources, appear widely distributed throughout the solar system. The oceans that sustain life on Earth, therefore, represent more than a local environmental feature. They may be the product of a long cosmic history in which water and organic chemistry circulated between planetary bodies before eventually assembling into the complex biosphere we now observe. From that perspective, the chemistry of life on Earth is not purely terrestrial. It is, in part, cosmic. Did you enjoy this essay? Let me know below. Like and follow for more.